So, hello everyone. This is Vicky from Dublin Maker. We have Laura from Tobin from Dublin Maker as well, and we have our maker for today as our maker a day as part of Science Week. Since Dublin Maker, we run a Maker Festival every year during summertime, but this year it's been because of COVID, we postponed it to next year. So we decided to um, we missed doing maker events, so we decided to do Maker a Day. So today, as our very first time running a virtual maker event, it's all experimental. So please bear with us if anything goes wrong. I suppose, Laura, would you like to say a few words about yourself before we move on to Spain?
No, I'm good, thanks. Best of luck, Spain.
Thanks, Laura. Oops. Oh no, I died. I played this game. I don't know if you can see me on the camera's not fabulous to see the game, but this is a little game console that we're building today. And it's based on, I don't know if any of you, well, I know all of you, you've had Wi-Fi problems and Google Chrome shows you the dinosaur games. With my students, the dinosaur game is a favorite. So I thought it'd be really fun to build a console based on the dinosaur game. Now my game is a little chicken because of course, as you know, a chicken is a dinosaur. I made this tiny little console. This one is made with a little digispark. I don't know if any of you have played with digisparks, but they are these minuscule little Arduinos. But the workshop that I'm going to show you today, we're going to start off because a lot of you might not have some of the modules necessary to make it, to minimize it. So I'm going to start off, show you how to do this just on a normal Arduino Uno. And then we're going to get into minimizing it and trying it with a nano, and then of course with the digispark like I did as well. But before I get into that, I just want to talk about the technology and behind an LCD screen, because I think it's absolutely fascinating.
And Spain, before you move on, before you get started, I just want to remind people that you can actually ask questions as well. So do so on our live chat here on YouTube, and if we may or may not have a break in the middle where Spain can ask if Spain is available to ask questions, but we definitely will have Q&A after the session. So please chat and ask your questions on our YouTube channel on live chat. So I'll leave it to you, Spain, and I'll just give you a bigger screen so you can actually show your workshop.
Okay, Grant, thanks. So, there's a bit of a delay I can see on the, watching myself on the YouTube at the same time. I see there's a bit of a delay there. So it's a little, so anyway, as I said, I want to talk about how LCD screens work, because I think the science behind them is really fascinating. And I think it's worth, talking about how an LCD screen works. So I think most of you know about polarized lenses. A polarized lens takes the light waves, and sort of puts them onto one plane. So it's kind of like, I don't know, have you ever seen those glasses with the stripes? They're not the most fashionable, but they're very cool because they shade, half of the light out. So like that, a polarized lens filters the light through chemical molecules and makes it go in one direction. Now, if you were to take a second polarized lens and turn it the opposite way, of course, that would stop all the light. What liquid crystal is able to do is liquid crystal can actually turn the light so where we want, the light can go through the second LED screen. So it's a really, really interesting technology. It was first discovered by Frederick Renitzer. I don't know if I'm pronouncing that right. I'm sorry if I'm not. But he was messing around with some carrots in the 1880s, and he discovered that as he heated it up, as he was heating his compound up, he found that it first of all became clear, and then it first of all became cloudy, and then it became clear. And so we realized that there were, we always talk about the three states of matter, the solid state, the liquid state, and the gas state. So for example, if we were talking about water, the solid state, as a Canadian, I know a lot about the solid state of water, a lot of ice and snow in Canada. And then obviously the water state and then steam state. But he discovered, of course, that there was this other state, which is in between the liquid state and the solid state. And basically the molecules are rod-like, and he also discovered that, you can use that to manipulate light. So it's really, really interesting technology. So, so without further ado, let's get on, and I'm just going to show you the project in the Arduino Uno. So I'm just going to switch cameras now. One moment for that. So I'll just go to, hopefully this is going to share now. Okay, so can you all see that okay? I hope you can. It should be my screen share, should be there now. So this is the project that we're doing with the Uno. And you might be thinking, oh my goodness, that's a jumble of wires. It's a lot to look at there. But it's actually not as complicated as it seemed. One second. I can't get a full screen. So I want to share something else. So 1 second for a second. I go into this. So sorry about this. I'll share something else here. So I'm going to share another screen to go over what we're doing here. So these are the pins on the LCD screen, and as you can see, both ends of the LCD screen are just powering the LCD screen. So on the left hand side pin, if you look at the picture, pin 1 and pin 2, those are just the voltage, the power for the LCD screen itself. Pin 15 and 16, those are powering the backlight on the LCD screen. And then we have our pin 4, 5, and 6, and these are communicating with the computer. Now 4 and 6 are going to go to pins 11 and 12 on the Arduino. And now that's very, we've just selected this, and you'll see when we're writing our code that these are just pins that we tell the liquid crystal library to use. Pin 5 is just we put that to ground because pin 5 is always showing. Well, in this case, we're always reading from the Arduino, so we want to have that always to 0, so we send that one to the ground. And then the data pins, all the remaining ones are data pins. Now you could use 8 data pins, but in this case, the LCD library allows us to just use 4 data pins. So we're using 11, 12, 13, and 14 for data pins on the LCD screen. And as you'll see in our code, we're connecting those to pin 5, 4, 3, and 2 on the Arduino. But again, as I say, you don't have to use these pins. This is just what we're using in this particular project. If you change the pins, you just have to change the information, and you'll see when we're doing the code. So it's really not as complex as it seems. I'm going to go back to it for just 1 minute and 1 moment while I go back to sharing that again. So as you can see, the other pins, the other thing that we have on this is the, I should actually plug this in so you can actually see it working. Sorry about that. Oh. Actually, I can't plug it in right now because I have, I can't plug it in right now because I've got the ports used up for the microphone. But as you can see, the other part of the connection is the button. So if you look here, we have a button here. So that's just simply, we have the a button which is using a drop down, a pull down resistor. So how a pull down resistor works is, I don't know if you know about this, but when we're using Arduinos, very often if we're getting a data reading off the pins, and we don't have a drop-down resistor, we get these strange readings that might go on and off and on and off and on and off. And that's because in the air, there's a lot of electric current, and the Arduino picks up that electric current from all the devices around us. And so if we don't have a drop-down resistor, we get funny readings. So basically all that drop-down resistor does is it pulls the current down to 0, down to ground. So so it makes us it allows us to have a clear, clean reading on the button. So it's a very simple circuit, as I say. The other thing we have here is on pin 3. I didn't talk about pin 3. I talked about 1 and 2 for powering the LCD screen. What the third pin does is it controls the contrast in our screen. So the reason we have a potentiometer here is that we want to be able to adjust the contrast in the LCD screen. So in theory, you could take this out if you find the exact resistance that you want. You could take the potentiometer out and just use a resistor here to minimize your project, but I've never really had very good luck with that. You know, I think it's just easier to use a potentiometer. A potentiometer, of course, is just a variable resistor. So as you turn the nozzle, as you turn the knob here, as you turn it, the resistance goes up and down as you turn the knob, and so you can see the resistance adjusts the contrast, so that the lower the input, the sort of darker it is for the display. So that's all there is for the display. So for the Arduino Uno, now I'm going to go on and show you how we can make this a lot smaller and with a lot less wires. So I'm just going to take this one away. I'll put this one in here. And while I do that, just 1 second. Now. There we go. So now here we go. So I don't know if you can see this, but this is our I2C serial adapter. And so basically, we can talk about how data is transferred with the why we're using the I2C adapter serial board. Basically, if you think about parallel, there are different ways. Just imagine for a minute that you were a computer and you needed to talk to another computer or any other device. All you have is electric current to communicate with. And so most of you will know that computers run by turning power on and off at a really rapid speed. And so maybe if I were communicating, I could send, there are 3 different ways basically that we could communicate to another device. One, we could send, 8 or 4 in the case of the Uno, bits of information all at the same time. So kind of, you could think of it as like the greyhound races. If you're at the greyhound races and you are, the dogs at the greyhound races, and then, the whistle goes and they all go at once. Well, that's kind of like parallel communication. Another kind of communication is serial communication. And so that means that one after the other, the data is sent one after the other. But if you're another device, you have to know how to break up the data. Whereas, what is the difference between on or on, right? How do you know where, which is on, which is off? So you have to know by the timing is the best way, the most common way to do it. So if you were to use, I think many of you will know UART. It's a universal asynchronous receiver and transmitter. So you are a receiver and transmitter. So simple, those words, but there they lost. So if you're sending information through UART, then both devices will need a clock. So the Arduino would need a clock, and the device that picks it up will also need a clock. And that's one way. And so they might say, we'll send information at 9,600 bits per second, which is a really common speed to send information at. And so they'll know, they'll chop it up in these blocks. They'll also send a start and an end bit so that the device, so you can make sure that you're sort of synchronized. But if your receiver clock or is in any way out from your sender clock, then your information is going to get garbled. So it also takes a lot of, because of the start and end bits, it takes a lot of extra information. So it's a slow way of communicating. So the other way, the way that we're going to use the I2C means of communication is kind of cross between the two. What that does is it sends a stream of data in a serial way. However, it doesn't require a clock for the second, for the receiver receiver, because what it does is it has one wire where it sends the data and another wire where it sends the clock. So it's kind of like a little drum beat. If you think about the drum beat, every time the drum beats or the electric current beats, then it knows if it's high, it will receive data, and if it's low, it will send data. So it's a really interesting and useful way of communicating, because it synchronizes the information transfer. So that's why we don't need, in this case, we don't need a 4 wires. We don't need to send all the information at the same time. So we can send it, through this I2C serial interface. So let's just take a look at the wiring of this. If you see here, and I'm just going to see if I can hold this up. So this is a nano here. I don't know if you can see this. So if you can see now, the first, turn this up to the camera like that. Yeah, that's a little bit better. So you can see that that we have the ground and we have the 5 volts here to run the device. And then we have the clock is on the outside, and then this purple one is the data. So that is going to pin A4 and pin A5 on the Arduino. And of course, this is the ground, and this is the 5 volts sending out here. So by doing that, when we send it through this library, and when we can then connect this up to our LCD screen. Let's see if I can get that in there. There we go. Now I'm not going to. No. There we go. Now, so that will, and let me just, what I'm going to do is I'm going to. You may have not heard me for a second there, but so, whoops. Now. Okay, can you hear me okay? Did we lose sound? I'm not sure if we lost sound or not. So hopefully we're okay. So now I've only got this temporarily put in here with a little bit of, there we go. So I've only popped that in there with a little bit. And hopefully that's going to work. See if that's connected there. There we go. I don't think you can see it anyway on the display. The display is quite bright now. The other thing that this has is if you see here, we have our potentiometer built right into the I2C serial module. So that allows us to adjust the contrast. And because I don't have it soldered on, I want to reuse this LCD screen. And since I've already made one that I've soldered on, I didn't solder that on. Now, as I said, we need to determine which wires to put the clock and the SDA or the data wire to. You just have to Google your device. Now, if you have a nano, it's going to be the A4 and the A5. So which one is the data is A4 and the clock is A5. So I can't actually see it here because my eyesight isn't good enough, but it's data is A4 and clock is A5 on the nano. The digispark, the data is D0 and the clock is D2, right? But what you need to do is if you have any other device is just Google the device and the pin out and look for the clock and the data pins, and they're all, it's very easy to find that. So without further ado, I want to go and take a look. Maybe before I get into the code, maybe this will be a good time to take questions if there are any questions. Does anybody have any questions? So what do you think, Vicky? Is it a good time to take questions?
Yeah. So I don't think there's any questions so far.
Before I get into the code, would you?
Can you hear me?
Is anybody anything they want to ask me about this?
Hi, Spain. Can you hear me?
Wiring?
Spain, can you hear me?
Oh, I'm not able to hear you, Vicky.
Okay. So can you hear me now? Can you hear me?
So
can you
sorry,
hear
Vicky,
me or down? Oh, Spain can't hear me. Okay.
I can see that there are some questions here. Any questions?
Um,
So I can
is
see
it a
the
DIY stand? Hold on.
this is the
So let me do a chat thing, given that we're
well,
having some issues
if there
here.
are no questions, we can take questions at the end if anybody has any questions. So, oh, there is one question I can see. Unfortunately, I just can't hear what Vicky has to say. So it's oh, is it a DIY stand? I'm not quite, I don't quite understand that. What do you mean by that? A DIY stand? Oh, the golden card. Oh no, I just use that. The card is just a piece of cardboard. Actually, I don't know if any of you know Recreate. You can get lots of this card at Recreate. And I this isn't really a stand. This is actually just because I didn't want to solder the LCD screen to the I squared C serial adapter, because I've already done that with the other project, and I don't want to go through another, just being cheap. Okay, so this is just to wedge it in place so I can demo it and so the kids can see it. So yeah, no, the golden card is just a piece of cardboard from Recreate. So sorry about that. Hope that answers your question. Any other questions? No questions. Okay, so let's talk about the code, because the code is really the fun part. For me, I'm a coder. My background is in coding, so this is my favorite part. Now, I don't know if you saw when I was playing the game that it was a very, very slow game, and I did that on purpose because I want to give you all the opportunity, and my students most of all, the opportunity to change the code to their own way. I'm just sorry, I'm talking to you and I'm also opening the code up here. So let's talk about, this is the, I was gonna say that all of this code is available for you on GitHub. If you just wanna Google GitHub and then Ripcoder and then Arduino _game _console dash, you'll see that the three different programs are there, and the difference between them is really minimal. From the first the first few lines are different, but after that there's very little difference. So the main thing I want to talk about with Arduino is if you're using an LCD screen, and remember I was talking about the wait a second, I want to see if I can annotate this. No, I can't. I wish I could annotate. Oh, maybe you have me set so I can't annotate. But anyway, so anyway, say looking at the liquid crystal line, I should have the Arduino doesn't have lines like most other environments, but the liquid crystal. So what we're doing here is the first line we're doing is we're bringing in the liquid crystal library, and the liquid crystal library does a lot of things for us that so we don't have to do it ourselves. It sort of sorts out the data and sends it off. And then, like, one of the things that I mentioned was that it allows us to send four lines of data instead of 8 lines of data, so that's very handy. So what we're doing when we're setting up, we're creating a new I don't know if you can see how I highlight this. Does that show up when I highlight it? I'm not sure if it does. So when we're bringing in the liquid crystal, we're telling it that our data and our clock pins, we're explaining what those, which pins we're using, and then we're telling it which data pins we have. So as you know, we're connecting the LCD screen to pin 5, 4, 3, and 2. And then the next thing now, so the way that the game works is quite simple. It basically displays a character, and then if the character, in my case, a chicken, and then if it's on the bottom line and the cactus comes along, then the 2 will be on the same line, and so then game is over. So one of the things that the LCD library has a couple of really excellent functions. One, of course, is print. So if we use, I'm going to scroll down here. So down to the end. Here we go. So you can see when the game is over, it's going to, let's just see. Here we go. So here we go on this line here. We can see that basically we set the cursor for all the information that we're doing. We set the cursor and then we print if we're printing a string. So for example, when we print game over, we use print. Now the other thing that's really fun is that we can use write. And what write does is it writes an array of bytes. And this is where we're going to create our characters. Now I'm actually going to show you, I'm going to go back onto the screen share and show you, just give me 1 second while we move over. I'm going to show you how we're translating the binary into characters. So one moment and I'll show you. Oh, I didn't get that ready today. Let's take this out of the way. Oh, well, just take this out of the way. And I'm going to share the camera again. So 1 second while I go to the share the camera. There we go. Now, whoops, sharing the camera, hopefully. Okay, so here we go. So here we have a little piece of graph paper. So if I start here, and now there's 5 across, 1, 2, 3, 4, 5, and down here 1, 2, 3, 4, 5, 6, 7, 8. Now, all of these lines down here, stand up for this one. So standing up here, not very good at drawing straight lines, am I? So if I wanted to draw my chicken, I might go with 0, 0, 1, 1 here, and then dot here, and then let's just see. I have, say, I want to have a beak here, so I'd put 1 here and 1 here, and then maybe I'd have 1, 1, 1, 1, 1, and then down here, and then down here. So you can see that it's kind of taking on a chicken-like shape here. I think I've done that, not quite the same, but all we do is for every square we want to fill in, you can see that for every square we want to fill in, we put a 1. Otherwise, we have a 0. So we can write this in binary. It's also possible to write this in hex and translate it, but for now, we're just going to do this in binary because it's so much clearer. There we go. So these guys here. So that's how that works. So the first line, let's go back to the code. So that's kind of going back to the code here. So you can see how this is the same chicken that I drew on the graph paper. Does that make sense to you? I hope that makes sense to you. So so that's so then once we've created these characters, the first thing we need to do is we need to use the LCD function create character. And then I've created the cactus, the chicken, the cactus, and then I also created a chicken upside down so that when the game is over, when you lose the game, it shows you. It shows you the game upside, it shows you the chicken upside down. So I created arrays here, byte arrays, and then I created the character using the name of that array, and then I assigned it to the assigned it numbers here. We're going to, these numbers 0, 1, and 2, you'll see when we are writing byte down here, write byte 0, that's going to be the chicken. So we set the cursor here and then write the chicken, okay? Now, we take the input. Let's go back. So the other thing we do is we have the button. Let's talk about the button. So when we get the input from the button, just like any of you who have used Arduinos before, using the input. So first of all, you have to set the pin mode for input, and then we get, now I have here digital read. So when the button pin is pushed, then we'll get a value, either it's a Boolean value, so it's going to be 0 or 1. And so if the pin is pushed, then we're going to see, we're going to move the chicken higher in the game, on the rows, so, or on the rows. So we'll say, here we go. So all right, so we've got, so here we go, and we say that if the cactus position, so we created a position, and minus is line 3. So if the cactus is at the same position as the chicken, and the chicken is on line 1, which is the bottom line, then the game will be over. Otherwise, we'll give you a score. So that's how the code is working there. So I think that there's not a lot left of the game to do. It's a very simple code. As I said, it's on the on GitHub. Now I'm just going to show you the difference. So if you are going to let me see if I can go to. Now I just changed to the other Arduino one. So I'm going to show you the code, the difference for the code now. So now this one, we're looking at the slight difference between liquid crystal setup and the liquid crystal I2C library that we'll be using. Notice that we're also using the wire library because we're communicating between devices and serial communication. We need to include the wire library as well. So that's one of the other differences. The other is, instead of just the liquid crystal library, we're using the liquid crystal I2C library. So so you'll need to use a different library there. And then instead of setting the different pins, we just have to we'll set the address of the device. Now each I2C device has a different address, and your manufacturer will, when you buy your I2C, the manufacturing information will tell you which library it is. And then we have to say the 16 tells you how many rows across, and the 2 tells you how many, sorry, the 16 is the columns and the 2 is the rows. So 16 across and 2 up and down. So that's what that does. So again, one of the other things that I did here was so that's the only difference in this. I'm just going to go with a slightly different one. So we'll take a look at the, for the tiny, here we go. So here we go on. So taking a look at this is for the A-Tiny or the digispark. So if you're going to do this with a digispark, then you'll use the slightly different, instead of the wire library, you'll use tiny wire library, and the liquid crystal I2C is the same as again. So I've defined the address outside of the instead of, and there's no reason that I did this. So, but if you're wondering why did I do that, why did I change the, why did I make a constant variable to hold the address of the I2C, and there's really no reason, because I'm only using it once. There wasn't any reason I did that at all, but I just did that. So let's see, start speed. I created the start speed, a variable to hold the start speed. And the way that this game works is each time you loop through it, each time you go past the chicken, each time the cactus passes the chicken, the start speed will start off at 1 second or 1,000 milliseconds, and then it'll go down by 10. So it'll get faster and faster because the the delay will be shorter and shorter. So I hard coded those up at the top because I wanted to make it easy for you to change it yourself. Most of you will have thought, wow, that game is really slow. And I actually did that for two reasons. One, because I'm really bad at the games, so I wanted to make sure that I could actually do it. But the other reason was that I want to give you the opportunity to, I wanted to keep this game really, really simple so that there's so much that you can do with it. This game can, could be a Flappy Bird game. This game could be, so many, it could be a leveler. It could be, so many different ways to change this game. And with the code, I kept it extremely simple. So I guess I would love to see, what the rest of you, what you do with the code. That's what I would really like to see is, how can you change it? And I'd be delighted if you want to contact us at Ripcoder, either, on social media or email. We'd really love to see what you do with this code. Like, how do you change this game? I'd love to see you mess around with characters, because I bet you could do animation with your characters. Like my chicken could be, putting his head up and down so simply. It would be very, very easy to, to have it swap back and forth, between characters to create animation. You could obviously create your own characters, and there's a lot you can do with 5 by 8 pixels. So I'd really enjoy seeing how you can change this game. Presumably you're going to want to make the game much faster. And maybe you want to go with different levels, because you could certainly easily go with once you get to one level and get to a certain point, you could level up. So I'd really be delighted if you want to share with us any changes that you make or anything that you do. I'd be really happy with that. So I think with that, that kind of goes over all the code and everything you need to know. Let me just go back to remind you that if you go to GitHub, and I'll just show you again the address there. So and back to the original one. These, as I said, these are all. So here again is if you want to take this code, the code, as I said, is up on GitHub. So it's github.com/ripcoder and then /Arduino _game _console capitals with the A, G, and Z. So if there is any questions about that, anybody have any questions, I'm happy to answer them, but that's kind of all I have to say for now. It's hard to talk for 40 minutes straight without feedback. Anybody have any questions at all?
Can you hear me? No.
Oh, here we go. Let's see. Would it be hard to add sound effects? It depends. If you're using, absolutely, using sound effects will be very simple. It wouldn't be hard at all to add sound effects. It's a great idea, a really good idea, and I'd love to see what you do with that. That's an excellent idea. We use the sound library to do that, and I did that on a project. I did a project where, I don't know if you saw at the Maker Lab a few years ago. I have a device, an Arduino device, where we measure the resistance of through some fruit. So you stick the knife and fork into two pieces of fruit, and then you guess which one is the most resistant. And then we used it to play a little song, as it it would play a little song when it was if you're correct in your guess. So so just a little speaker. Now you'd need a little speaker though. I suppose what you could do is you could use a you could have a little speaker. I think I'm just wondering how you would have it, or you could probably design something. There's so many ways to amplify sound using, cups and things. It'd be really fun to see what you could do with that. And it's a great idea. Anyone else?
Is there any more questions? I don't know if Spain can hear me. I'm just going to post a message to on share screen first. Sorry, I'm just text chatting over Zoom.
There we go.
So you can't
Any
hear
other
me?
questions?
You can't hear me? Folks can hear me.
So I'm seeing Vicky, that's why she's saying, can you hear me? I can't hear Vicky, so that's why I was making that funny face. So
Laura, can you see if you can actually, can she hear you, or is it just me?
Hi, Spain. Can you hear me?
all right. So
Okay,
any
I'm just
questions
gonna.
at all?
Oh, okay. Spain, can you hear Laura? Sorry, everyone.
People can't
Technical
hear me.
issues.
Okay, no worries. So I won't talk.
I suppose we'll have to type
anyone.
our chat. Go.
Speaker. I wonder
So Jeffrey asked, "Do you have any debouncing problems?" Okay, there are a few questions.
I don't hear anyone.
I'm sorry about all the typing, so I will be typing and chatting. I just have a clacky keyboard.
Oops, sorry. System. Yeah, no, I don't have any sound. Sorry about that. Anyway, I have no idea what you're saying, Vicky. So you can, okay.
So this is from Frank.
Okay, from Frank. Do participants build enclosures? Oh, I meant to say, actually, thank you very much for that. Yes, what we do is we have, of course, a 3D printer here, but not everyone has a 3D printer. I put the files up of the little box that I have here. Let me just show you this little box. Now, this box is a really simple box that I made, and we just 3D printed that. I made it large, a little, place for a button here, and actually, as you can see, it's kind of, I haven't put it all together there. That's the insides of it. So we're going to glue it after the kids are done the project. But what the students are doing is they're using Tinkercad. You could use Fusion 360 if you want, but for my students, that's very complex. So we're using Tinkercad, and they are making these amazing, really, really amazing enclosures. One of them is making it in the shape of a hand. It's really funny. It's so funny. Yeah. So I'm letting the kids design their own. Like, what if you were, 10 and you were making a handheld game console, what do you think it would look like? Well, I had no idea what it would look like, but these are so cool what these kids are doing. They're really brilliant. So hopefully I'll show them on social media when they're done with them, if they allow me to. It's completely up to the kids, of course. But yeah, no, what they're doing. And so then we're going to 3D print ours, but the libraries are a great resource. And I know they're not open right now, but most of the libraries in Dublin have amazing 3D printers, and most of them are more than delighted when you come in and ask to use them, because that's what they're for. They're for the public. And I don't know if enough people are using the 3D printers. So now I apologize to librarians all over the city if I'm wrong on this, but I think that they really like it when you come in and want to use their 3D printers. So, because they all, I think have great 3D printers, and they are for public use. So you should design them. You could, as I said, I popped the G code up. G code is the code that you use for a 3D printer, and I popped that up. And so that if you want to use mine, but mine, of course, is not as exciting. I recommend that you go to, get onto Tinkercad. Tinkercad is free, and have some fun. So do you have any debouncing problems? I'm not quite sure what you mean by debouncing. You mean when it restarts the game? Are you thinking? I'm not sure. When I drop it on the ground and it bounces? I'm not sure. So, do you want to be clear? Do you want to say that?
Oh, one more question.
Explain again. Would it be hard to add sound effects to this game? Yes, as the question was asked before, and no, it would be really easy to add sound effects to this game. Really, and it's a great idea. I wish I had thought of it before I did this, and maybe I'll add it with my own students, because it's a brilliant idea. And adding sound is really, really not hard at all. So we've done it before, and it's very simple. There's a library for that. but I'm not sure what you, to be honest, he means the button press. The button, no, I think, kids are used to buttons that's more responsive. Now with this one, you really have to hold it down because I have it timed out, sort of timing out, so you have to sort of, it has to be held down for the second or whatever the speed is. So yeah, no, you do have to hold it down. And it's actually, I have a game console here, one of those retro game consoles that I made from a Raspberry Pi, and the students find, getting used to when you're playing Pac-Man, you really have to yank it down. But that's the way that games used to be back a million years ago when I was first playing video games. So, they are kind of a little reminiscent of the old games, but yeah, no, I mean, it's certainly, it's just it's a tiny little thing, but yeah, I think that's no, it comes straight back down again, no problem using the code. I think it's no problem, but as I say, you do have to press that button.
Sorry, I am typing away here to her. So if anyone has any more questions, just let me know. I'm just saying there's no more questions. Just ask her if she have anything to announce before we wrap up. We have a few minutes. We have 3 minutes left, so.
No, I think I don't have anything to announce. I think that's it, really. I think it was really fun to do this, and congratulations, Vicky. Thanks very much, Vicky, for having Ripcoder Club on your Science Week Maker Week. So I'm really delighted to be here.
I'm just saying that we can still hear her. I'm just apologizing about the audio.
Can you hear me okay?
Yeah.
I hope you can hear me.
Yeah.
So
and I'm just saying her that it's
yeah, we can still
really
hear you. Oh, good,
enjoyable.
very good. So I won't burp or anything. So anyway, thanks very much for having Ripcoder Club. It was great fun to share this project that the robotics class is doing, and I wish you all the best on your Maker Day week, and we'll see you soon, I guess. Is that okay? Oh, one more question before we go. Great. Okay. Okay. One more question. Oh, very good. So I didn't actually, in this one, actually, this is great. And I'm glad you brought this up. Now, this one I have here, which is running off the Arduino, this is running off the digispark. So I can actually run this. I'm just using a little power bank. And this is just a power bank. It has some the little lithium ion. Now, I don't give my students lithium ion batteries because in my experience, here we go. So this one, so you can see this one running here. So this one, the digispark, I can run off of a little power bank, but I didn't build in power into the program because, one thing, I often have power issues and that can be a real pain. So to be sure with the Nano and with the Arduino, I think you're going to need to use, a USB connection to the mains or to a laptop, something that gives you enough power. But with the digispark, you can power it off some of the lithium ion batteries. But, as I say, I don't like to send those home with my students because they are lethal and I've had fires before on them. So I don't send the kids home with anything that's going to burn their houses down. So that's just a policy that I think is a good one. So.
Good.
Okay.
I'm just saying that
All
we're
right,
going to
I guess
wrap up.
that's a wrap. So thanks very much for having me, and I hope you enjoy. I'd love to see if any of you do this project. I'd be so interested in seeing what you do with it, because I think that there's the reason I picked this one for you is that there's so much scope for you to play with that code, and playing with the code is the fun part, really, for me anyway. So obviously it's nice to see it in real life, but I think, there's so much here you can do with that, and it's so easy to change this. So please let us know what you do with it. And thanks very much to Dublin Maker, to Vicky and Laura and Dublin Maker for having Ripcoder Club on. Thank you.
Thanks so much. Yeah. Bye.
Bye-bye.
Just as we wrap up for this session we are preparing for our next one, which is with Frank Duignan. Hopefully I say his name right, from IO Prague. He'll be showing you how to make a Dublin Maker Badge and a digital badge. So yeah, we'll see you in a few minutes. We're gonna swap over. I'm gonna put you on intermission. And thanks again to Spain from Ripcoder, and to Laura. Sorry about the audio at the very end. She couldn't hear us, but apparently everyone can hear me fine. And yeah, we will put up that GitHub link as well. So do share your creations, and share it with us, and share it with Spain especially. All right, see you in a bit. Hi everyone, welcome back to our second session of Maker a Day. And we have Frank with us today, who'll be showing us how he made the Dublin Maker Badge, the digital one from last year. And I still have it, and I think Laura does as well. and now if you have any questions, and he'll also be showing you your plans for the next one, new improved one, right, Frank?
Okay,
Oops, sorry.
there's a bit of a lag
I don't
there.
know. Hold on. Give me a second. I don't know what's going on there.
There's a lag of a few seconds.
Yeah. So, okay. Sorry, there was for some reason, my YouTube channel went off talking by itself. So if people heard that, that's just me. Technical issues. That means it's live. This is great. So anyway,
Okay.
So again, this is me, Vicky, and Laura from the Dublin Maker team. For those who don't know, we run a Dublin Maker Festival every year, but this year it was cancelled and postponed to next summer due to COVID. So we decided to do a bunch of smaller events like this Maker a Day, bringing makers around and giving workshops and demos. And if you have any questions, do put them down in the live chat in our YouTube stream. Frank will be available to answer them after the session. So get those questions on live chat, and also our hashtag is Science Week Maker as well. So without further ado, Frank, is it okay that we will show your session now, and then we'll see you back in a few?
Okay.
Righto.
See you later. Hello, my name is Frank Duignan. I'm a contributor to Dublin Maker, have been for a number of years now, and along with my colleagues over the past, I suppose, 7 years, we've run a stand in Dublin Maker at the various venues. It's been hosted, starting in Trinity and then lately in Herbert Park. Sadly, 2020 didn't happen due to COVID, but here's hoping for 2021. Anyway, in 2019, I began to consider making an electronic conference badge, an unofficial one. It didn't have any official sanction on this, it was just a part-time hobby thing. And I had a look at various badges that were around. I wanted to see what I could make cheaply and yet still be reasonably capable. So here's a look at some of the conference badges from various conferences around the place. This is DEF CON in 2016. It had a badge with 2 gamepads on them. There was a microcontroller here in the middle and a battery driving the whole thing. Most notable thing about the whole badge was the skull-shaped PCB. 2017 was more obviously a game type device with an LCD display, another gamepad, LEDs above and below the display. Well, these would be multicolor LEDs, and some status LEDs on the right here, plus a speaker and a port here that you could expand out the game to add on additional external hardware. DEF CON 2018 featured an unusual PCB which is shaped like Bender from Futurama in a kind of a dystopian sort of way. I suppose it's merged with Terminator. There's a display here where the game output goes. There's a gamepad over here on the left. And there's a whole bunch of LEDs along the rim of the hat here, more buttons, and it was able to communicate with other badges. Plus there's more expansion capability along the bottom here. DEF CON 2019 was in, I suppose, commemoration of the lunar landings that took place 50 years previously. The badge itself was actually shaped like the lunar command module. And the games featured a lunar landing theme, and you could see the sort of LEDs to indicate the rockets being fired on the command module. EMF Camp is a camp that takes place in Britain every 2 years. EMF stands for electromagnetic field, and its badge of 2018 also had a game theme. Lots of expansion capability here with these little connectors around the place. A joystick, a miniature joystick here, some buttons, and a numeric keypad. Badges typically like this have some sort of electronic game, and they're often sort of retro arcade in nature due to the fairly limited hardware. Unlike a PC which might have several gigabytes of memory, these typically have several tens of kilobytes of RAM, perhaps even less, perhaps even just a few kilobytes. They tend to be sprite based, like this is an invader sprite here. This is a sprite like a little I suppose a dog, I guess. And then this one here is a running boy, and the sprite in this case, the way you'd use it was you'd flick between images here and generate the impression of somebody running. So it's like a live action video, but made up in fact of 6 separate frames that are just cycled through. Badge expansion is a big thing. This one here has a prototyping area. These are just holes with metals going through them to allow you to solder or else wire wrap it components onto your badge. And along the edges here you see a power supply, 3.3 volts and ground, serial data and serial clock from an I2C interface, which is a data interface commonly used between microcontrollers. There's another variation of it here, just simply showing 4 holes here for power supply, plus, ground, data and clock. Some badges can be quite expensive. This one here features a lattice semiconductor FPGA and a display, and looking at the bill of materials here, it probably ran close to €100 per badge. So it's quite an expensive badge, and not one you're going to give away for free to large numbers of people. By contrast, this simple badge here, shaped like a rocket, was given out in kit form. Very cheap badge to put together, or kit to put together. And then there was a workshop in the maker camp to show people how to solder the badge together, and they left with a working badge that they could have an LED on. Dublin Maker of course has had a badge for, I think, every year it's run. I have a few of them here. This was an early one made from plastic. I think it was laser cut and assembled by way of a kit. Reasonably expensive and complicated to do that. In later years they went for a more, I suppose, environmentally friendly wooden badge like this, where you just laser cut out the wooden surround and laser etched in the Dublin Maker logo and the date of Dublin Maker itself. So in 2019 the electronic badge looked a bit like this. It had 4 games in it. And a Space Invaders type game, or kind of like Galaga type game, which you could play with the gamepad here. It had a breakouts like game called Bricky, which is the Irish for bricks, and had a tennis game, which was a 2-player Pong, which you played by connecting your badge over this cable to somebody else's badge. So this cable here doubles up as a lanyard and a data cable to connect badges together. There was also, in the last remaining bytes of memory in the chip, a Moonlander game, which was pretty primitive, but because Dublin Maker 2019 landed on the same day, or 2019 on the same day as the 50th anniversary of the moon landing, couldn't leave that one out. The total cost for this badge in materials was about €4.66, not including the battery, and it used a single AA battery on the back. Here's a bunch of us building badges. It's Oren, Ted, Damon, Jeff, and Shane and Porrick. This is all in Tog one evening. We spent a few hours there, and there was a few sessions like this putting badges together because it was quite involved. There was soldering, gluing and wire wrapping involved, putting the whole thing together. Looking more closely at what was in that badge, there's a full color 240 by 240 display, so quite a high pixel density there. A power supply regulator which took the battery voltage and stepped it up to 3.3 volts. That was the operating voltage for the display and the microcontroller behind it. It was actually a very efficient little regulator, and it was able to continue to operate when the battery dropped down to about 0.9, 0.8 of a volt. So it really got the last out of the AA battery. Total life, it's probably about 8 hours on a AA battery. There's a programming port here to allow you to download programs onto the badge, and this was obviously pre-programmed for the day because nobody would be going around programming badges on that day. And then the headphone sockets here, they're 3.5mm headphone sockets that you connected the headphone cable to, or the audio cable to, which really ended up being a data cable. Okay. On the back of the badge, which is not very pretty, you can see this is a really cheap prototyping board, the cheapest we could get at the time. There's some soldering. Not a lot of soldering, they're all 0 volt connections all around the place, all those black wires. There's a piezo speaker here to make noises for the game. And then you can see some rows of pins here. This row and this row belong to the microcontroller board, which sits on the other side of this and beneath the display. And then these pins here are from the actual display itself. And these are connected in using wire wrapping. Now, wire wrapping is kind of died out as a technique here these days for building prototype boards, but it actually is quite nice to do. It's easy to fix up any mistakes you might make, and also you can disassemble your system at the end and reuse the components if you want to. So it's quite a green thing to do, I suppose. So this is the Dublin Maker 2019 unofficial badge in action. Boot it up and it shows you the Dublin Maker logo and a choice of 4 games. Bricky, which is like Breakout, Invaders, which is a bit like Galaga. There's a tennis game, which is a bit like Pong, and then there's a sort of very primitive Moonlander sort of game, because Dublin Maker 2019 happened on the same day as the first moon landing. If you don't press any button, the game goes into kind of demo mode and uses the Dublin Maker logo as a target for Breakout or for Bricky, and it smashes it up. Now if you press press the keys, so press fire here, it gets ready to start. Press fire there again, and right, so we can fire for Bricky. So I go here. I can do a Breakout here. I'm not very good at this while I'm recording at the same time. Okay, so you get the idea. It says Breakout. Ooh. Nearly got it. And game over for that one. Press fire to go over again. Then we have Invaders. If I go left here, and we can shoot at these guys. And we get so many lives. They're shown down the bottom right there, the number of lives you have available to you. Okay. The Pong game actually requires 2 badges, which is too difficult to set up for now, but basically you play Pong against somebody else, and it communicates over this interface here, which is sent over. The lanyard itself doubles up as a communications cable to link 2 badges together. In theory you could daisy chain multiple badges, but I haven't written any game to take advantage of that. And then the last game is sort of a Moonlander game that was down for Moonlander. And basically the idea is you're trying to land on the moon, and as you leave, the moon lander sitting there begins to accelerate, and you have to try and balance your fuel with your falling speed and try and land. Yes, we have landed successfully in the moon lander space. First time I ever got that, by the way. Okay, thank you. So this is an electrical schematic of what's inside the 2019 badge. The microcontroller was an STM32F030 in a 20 pin package, and that was a cost around about 34 cents. There's 2 resistors here to pull up the boot pin and the reset pin to high so the thing boot starts up properly. There's a transmit and receive pins here to send data over the lanyard to additional games. These are the programming pins used to program the chip. And then there's the various buttons used for the gamepad and the fire button. There's also a buzzer here. The boost converter or power supply regulator is shown here. It takes a 1.5 volt input and outputs 3.3 volts. And finally the display, it's based around an ST7789 display chip. Reasonably cheap module from AliExpress. Cost of the order of a 170, 180, that sort of price. Now, what lessons did we learn from 2019? Well, the sockets we used for the multi-gameplay were a little bit shaky. Any kind of jiggling of the game, which of course happens when you're playing a game, caused a ball to get lost as it went from one player to the next. Memory was very short. We had 16 kilobytes of program space and 4K of RAM, so very, very tight to fit all those games in there. There was also a lack of I/O pins to do additional things like expansion, because that was a 20 pin package we used. And overall it was quite a delicate final product. Lots of things glued on, wire wrapped on and so on, and didn't take a lot of abuse. So improvements that were planned from 2019, well, were first of all get rid of the wired multiplayer interface and use a radio module. This one here is a Nordic Semiconductor NRF24L01. It's a short range radio module commonly used for keyboards and mice, wireless keyboards and mice on computers, and also for some remote control drones, for short range ones. So it eliminates those sockets, which saves 28 cents in total, and it also eliminated the lead, which was about another 44 cents. So we saved, what is that, 72 cents altogether or thereabouts. The radio module itself cost only 47 cents. So really just a net saving here, which is great. And it was wireless, so people could remain, I suppose, socially distant, I guess, in these times. The microcontroller was also upgraded, and like a lot of computer stuff, upgrades come fairly quickly and prices fall. So going from our original chip, which is a 20-pin device, to this one here, which is a 32-pin device, and also has twice as much ROM, or program space, there was no price change. We just had a larger number of pins and larger memory for the same cost as the original. The big change from 2019 to now, to supposed to be 2020, was a custom PCB. This is what it's shown. This is as shown here. There's a space for the radio module. The microcontroller sits here. The display sits on top of it. Your gamepad goes here. Power supply module here. Programming port. Expansion port. The programming port, by the way, also can be used as an expansion port. Battery connections, switch, and there's a resistor here just to limit the current on one of the pins of the microcontroller. Now, while there was some cost saving due to the radio module, the PCB itself added quite a lot to it, and added €1.78 to the prices of the board. So the total cost now went up to €6.20 from the previous €4.66. So the expansion headers are just like in the badge life type badges we saw earlier, has an I2C interface here, and it also has a transmit and receive pin in between these two pins here, which are also programming pins. The power supply module shown here, oh yeah, the whole thing then was designed using an open source PCB editor called KiCad. Now let's look at designing a simple PCB using KiCad or KiCad. We'll begin by starting a new project, and let's call it test 3. Press OK. And you begin with a schematic. So we go into our schematic and we start putting components on it. Now the circuit I have in mind is just a push button, a resistor, LED, and a connector for a battery. So I'm going to drop components on the schematic here. This is an electrical drawing of our circuit, and I'm going to put an LED in first. So there's our LED, and drop it, say, there. So zoom in on that, and there we go, we have our LED. Now our next component is going to be right behind it is going to be a resistor, OR, and I can rotate that with the OR command and drop it in like that. Next command, is going to be the push button. So we're going to have a search for a button here, or a switch maybe. Switch. Okay, so switch, push button, there we go, push button switch. Drop that in there. KiCad or KiCad is quite a big library lately, so it can take a little while to find some things. And finally a connector for the battery. So CONN, and a 1x2 male is kind of a pin sticking out of the board. We'll drop that in. Okay, and I want to rotate it so it makes my circuit easier to draw. And there we go. So that's our components all dropped. Now we've got to wire them together. So you pick the wire tool, go from there to there, and there to there, and there to there to there, and finally around here, all the way around to here, here, here. Okay, so that's the wiring complete. And finally I want to assign a resistor value here. So I go in here and edit, oh, not the reference, I want to edit the value and give it a 220 ohms. Okay, so now we have a 220 ohm resistor or LED and so on. Now why 220 ohms? Well, it's quite a common value to use. It limits the current just the right amount when you have a 3.3 volt or 5 volt circuit and an LED. So that's this electrical part done. Now that really bears no relationship to the physical layout of our circuit. We need to begin now by assigning what they call footprints to the various elements here. So tools, assign footprints, and we click annotate, that we want to proceed with the process here, and it begins with our LED. We've got to pick a particular LED shape and size. So I'm going to go down here looking for the LED. So it's over here, it's alphabetically LED, and you see there's two types here, LED SMD and LED THT. LED THT stands for Through Hole Technology LED. It's the one that you push through the board and solder on the back of. SMD is for surface mount, which is a much smaller LED, and it's not one I really want to be doing in this example. So I'm going to pick there, and then what diameter? Well, I fancy a 5mm LED. Now the connector, it's over here, so connector, pin header, and it gives different separations between the between the different pins on the pin header. 2.54 or 0.1 inch is quite common, so I'm going to go with that. And if you're unsure, you can preview the pin header like this, or the component, by having a look at it there. So let me just move that down there. So that's not the one I had in mind. Come across here a bit. So I want pin header 2.54. I want a vertical one and a 1x2. So that's the one I have in mind. They're the solder pads that's going to be they're going to be on the PCB for this. Resistor, well, it's OR THT, or resistor through hole technology again. And the size, well, I think the one I had in mind is about a 1/2 inch long, which is 12.7, about there. Let's have a look at the size of that. Yeah, that's about right. Okay, and finally the push button. I'm going to go look for this now. It's in the button switch through hole technology, and we'll have a quick keep this on screen here so we can have a look as we go through these things here. It's going to be a momentary push button, so on that sort of spacing, what is it like? Yeah, that looks about right for the sort of thing I have in mind. Okay, so we've assigned all our footprints now, so we press OK, and we're good to go. So let's go to Tools, Update PCB from Schematic. So that converts that to a PCB. Update PCB, close. And we see all our components all kind of jumbled together here on screen. This is the physical view of them. So first thing I'll do is I'm going to pick them up and move them around a little bit. So we pick this one here. Okay, stretch it. I'm going to rotate it maybe one. Okay, I'm going to pick this one. Okay, put that there. Just spread things out a little bit. Put that over there. Okay, and now, so they're roughly where I want them to be. And the next thing I need to do is route the wiring, because the wiring that's shown here is like a virtual connection. It's not actual copper yet. You have to tell it exactly where to put the copper tracks. So you click there, and there is one copper track. There, there, there. It's another one. There to there is another one. And there to there. There's a connection inside the switch. Here to here is another one. Here to here is another one. And that's it, routed. Now, one nice thing about KiCad is you can view your board in 3D. So let's have a little look. There it is. There's our circuit. You can swivel it around, have a look, see, is that what I had in mind? You might decide, oh well, I want that jumper to be somewhere else. But it's a very useful tool for visualizing how your final board will look. Having designed your PCB using KiCad or KiCad, you now need to get it made. Now, in the past, people would have probably tried to do this at home using acid etching or some similar technique. It's reasonably cheap to do, I suppose, but it's a bit messy to keep all those chemicals around the place. And if you're not doing PCBs regularly, those chemicals can degrade. So it's not a very cost-effective way anymore to make small run PCBs. It's much more efficient to send these things away and have somebody else make them for you in a nice professional setting. And they also do things like to plate it through holes, which facilitates connections between layers on boards. This company, PCBWay.com, advertised that they can produce boards, 10 boards for $5 plus shipping. Now the shipping can be a good deal higher than that, but you're talking maybe 30-40 euros to get 20 or 30 boards delivered to your house. So you upload your designs to PCBWay. They actually require a particular type of design called a Gerber file, which KiCad can export. You say you want 10 or 20 or 30 of them, and then they array those on one big sheet of PCB. They make them and then they chop them up into the sizes that you want. So the process is pretty straightforward to get these things done, and there's some useful videos around the place to help you do that. So having submitted your order and paid your money, 10 to 12 days later, what arrives? These. Your PCBs shrink wrapped in a nice PCB weigh box. And I have to say I was quite surprised how quickly they came back. I have to be honest though that this was not the first attempt at this. I think it's inevitable that when you go to make a PCB, your first go will contain mistakes. So I'd really recommend, if you're doing this, that you go for the smallest run you can get away with the first time. Get them back, 1 or 2 boards, whatever it is. Try them out, test and build your circuit. And then if it all is okay, then order some more of them, or else submit your new design and go again. It can take several iterations. I think I've gotten away with it after just 2. Now, having got the PCBs back, you now need to go soldering to put them all together. And these are the sorts of tools you need for that. You need a temperature control soldering iron, a soldering iron cleaner, some small hand tools, some very thin solder because you're working with surface mount components, some solder braid here, which you can use to take away solder that's accidentally connected 2 pins together on small surface mount components, and some solder flux, which helps the solder to run smoothly along the tracks and helps to avoid accidental shorting of tracks to one another. I'm soldering the radio module onto the badge, and I'm going to begin by just putting a bit of solder on the soldering iron and bring that into contact with the pins of the radio module just as they meet the PCB. You've got to take your time with this because there's a lot of scope to get things wrong, because the parts are very, very, very tiny. Okay, and I think that's okay. I don't know if you can see those holes now. There's 2 there made. Note the piece of blue tack holding everything together while I get the soldering in place. It's important not to have the parts moving around the place. I've positioned the microcontroller on the board now, again using a bit of blue tack just to hold it in place while I get the first couple of solders in. You tend to put solders in which are kind of diagonally opposite just to hold it in place. And then once all the pins are correctly lined up, you say okay, take off the blue tack, and then we're good to go because it's held in place by the initial solders. What I'm putting on now is solder flux, and the job of that is to make the solder stick to the metal and not to anything else. So you carefully go in with your soldering iron. Again, carry a little bit on the iron, a little bit of solder, and gently heat the pins one by one as you go through. The trick is not to use too much solder because you'll end up joining pins together that shouldn't be joined together. So very gentle on the solder. You have to remember that your iron will carry some of it from joint to joint, so you don't need to keep filling it up. If you find there's too much solder on your iron, clean it. Let it warm up for a moment. Get in there. This is really essential to have a good well-lit magnifying glass for this sort of work. Okay, I'm getting in there. You have to wait till the solder flows and joins 2 bits of metal together, the pin of the microcontroller and the little pad on the PCB. So take your time, and I'll show you that side now. Okay, it's all soldered there. There's a bit of solder flux left on it, and I'll clean that off with an alcohol wipe. We're going to do some continuity testing now. The idea behind it is we're going to look for connections where there shouldn't be connections and making sure there are connections where there should be. The most likely place for accidental connections to occur is between adjacent pins. So if I have my voltmeter here set to continuity testing, if I join the wires together it makes a beep. So this is really convenient. So I place the probe in one pin or one hole of the radio module and go to the one next, and it should not beep. Move along one hole at a time, and should not hear any beeps happening unless I accidentally touch the probes. Okay, so it looks like I have no accidental short circuits. I need to do the same with the microcontroller. That's a little less easy because the pins are so small, but if you kind of sit at the top of them you can kind of get it. So you very carefully go through all these And I've also visually inspected these to make sure there's no accidental short circuits. Now that we've seen how the boards are made, here's an almost finished board. I haven't mounted the display yet because I'm going to do the testing, as much testing as I can without the display on board, because once the display is in, it's not going to be easy to get that microcontroller back out of there if there's something wrong with it. So the display will probably sit in here just temporarily without being soldered. I'm pretty sure that's going to work okay, at least for testing purposes. And all the other functions like button presses, sound and radio can all be tested without the display in place. Now, the badge software was written in C++. Why C++? It's not exactly the most user-friendly language, but it is very low level, and it allows us to fit a lot of code into a small amount of memory. Why not just C then? Well, C++ assists in the partitioning of software elements, and it kind of suits graphical based things anyway. I've always felt more comfortable with object oriented programming and for graphics rather than just procedural programming. The layout of the software is like this. It's in a layered approach. At the bottom layer here you have your hardware, where you have your radio, your display, your various buttons, the speaker and the extension headers to allow people to do additional things. They in turn have a software file associated with each of those. NRF24L01 CPP controls the radio, display CPP controls display, and so on. And they in turn then are made up into a larger object called a console, like a games console. Why do it in this layered way? Well, it allows you to swap out these different components here or change them should, say, the display change or should the radio change, without having to rewrite everything above. Also, along with console.cpp, there are another additional helper C files. There's one for managing sprites. These are moving graphic objects. And there's one for managing things like random numbers, which are essential really for gameplay. On top of that console.cpp, the game software is written. So here we see Space Invader. And it makes use of everything in the underlying layer, but it does not reach down to the lower levels, because that would break the whole partitioning scheme. Console.cpp is the lowest level the game software gets. This greatly helps in program portability and maybe extensions for future years. Now the software, I'll just give you a couple of snippets of what's inside. This is a sprite, as I said, a movable object is a sprite class, and it has methods called show and hide and redraw and move, and then some methods to test to see if a point is within the sprite or if something's touching it. That's useful in gameplay to see, let's say it has a missile gone inside the sprite and then it blows up, of course, or if it's touching the edge of some perimeter, and then you say, okay, it can't go any further. And you can also check to see if it's visible or not. So how would you use that? Well, you could, for example, check to see if somebody has pressed the left button by calling get button state of the controller object. This just checks to see if the left button is currently down. And if it is, you move the defender back left 2 spaces, which in this case here is -2 pixels, which shifts it along the x-axis 2 dots to the left. And you just check to make sure that it's not already as far left as it can go up against the left hand side of the screen. So defender.move makes use of that move method inside the sprite. So it becomes pretty legible inside the higher level games about what's going on. You don't need to worry about the lower level hardware details. Now, other little section here, it's the only other section I'm going to show you. If a missile ends up being within a defender, well, what do? Well, you hide the defender and you put an explosion on screen. And that explosion just calls this function, which makes a new sprite called bang, made up of an explosion image and at a particular point on the screen. You show it, you play some music by calling the play tone method of the sound object, wait for a moment, play another tone, wait for a moment, and then you hide the bang off the screen again. And at that point then the defender is missing off the screen. Now if the defender count is 0, if you've reached the end of your defenders in Space Invaders, well then you've nothing left, nowhere else to go, and all your defenders are dead, and you say, and up on the screen comes game over. and press fire to restart. So that's the level of C++ programming that goes on inside the game. It's not exactly plain English, but it's not too hard, I hope. Now, as well as the game code, you have gaming assets, and these are images, icons, tunes, etc. that are commonly used in games. The badge had some simple assets, a Space Invader sprites, for example, and they have to be represented on screen somehow, and a Dublin Maker logo that can be taken apart by the breakout game, so you can not just destroy little parts of it, so a static image isn't good, it won't work there. So the sprites were just written by hand, where the invader had a particular color that was defined in a symbol here, and you can make it an image in one of the C++ header files here. Here we show a defender image expressed as an array of colors. So we have background, 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 and then the invader color, which in this case here is red, and I think it's a cyan sort of color we have here. And if I highlight just the word invader, IVDR, in that array here, you can actually plainly see what the invader is going to look like on screen. So it's a nice handy feature helping you design in a text editor some of your images. Now for more complex images like the logo, that wasn't going to be possible. So instead Inkscape was used to make an SVG, a scalable vector graphics object of the image, and these are made of little bricks here on screen. And the nice thing about SVG objects in Inkscape is when you save them, they're saved as text files. Now, as a text file, you can further process that using a little bit of Python, like this here, to convert all of the output of the SVG file into an array of values that make up the bricks for the logo, and then that can appear on the game. This is several pages long, and it would take a lot to design that by hand. Using Inkscape and the Python conversion script greatly speeded that up. Now, lowering the hurdle. Well, all this is pretty complicated stuff, and C++ is really not for everybody, particularly beginners. So there are alternatives if you want to get into some simple gaming. Pygame helps you write games in Python. You write your code in the Python language, making use of a library that manages sprites and so on, and sounds. So in a way, it's kind of like the console object in C++ for the badge. Recently, Microsoft have produced MakeCode Arcade, however, which really simplifies game development. And what's more, it allows you to write games for electronic devices which are very like conference badges. And we'll take a look at that now. This is Microsoft MakeCode. It's a development environment to allow people to write programs of all types. It was a project set up by Microsoft to encourage people, old and young, to write code. And you can write your code in various different languages. This one particular language here is quite like, it's a block language. I suppose it's a bit like Scratch. But you can also program in Python, or you can program in JavaScript. So you can switch happily between all three languages, and they're equivalent in this setup here. If you find that the blocks language isn't expressive enough, you can switch to one of the more typed out languages like Python or JavaScript. Anyway, you can write games, and you can run them in a simulator here, which has a gamepad that you can move your character around in. You can drag the gamepad on screen, or you can use the arrow buttons on your keyboard. The programs are what they say is event driven, so pieces of code are run in response to particular events that may happen. So the first event that happens is when you start your game, you need to configure the whole thing. First thing is you set up your sprite, your player. So on start, set my sprite to this. Now, what is that? Well, it's something you can draw. You can change your character, or you can use a gallery, one of the off-the-shelf characters, and there's lots of them here to choose from. I've chosen to design this particular one. It just allows us then to play with different, I suppose, kinds of things. So I'm going to just change that bit to orange. Press done. And next time we look at the game, that center core there should be now orange, and indeed it is. So you can set your character up to be whatever shape or color you like. Next thing is you want to set your tile map. This is the map that the player runs around, and you set it to whatever you like. So this one here is just a maze type map, but you can have platforms that players can jump off of and so on. The red areas are walls, and the yellow blocks here are where we're going to put an initial set of baddies for this game. So the next one here is to get the camera to follow your sprite around the place so that it remains centered on screen. So as we go over here, the screen pans with the player left and right and up and down. Next block, make the background color red. And then this part here is a loop, a program loop, which goes through all of the yellow blocks that are in your tile map and replaces them or puts on top of them a sprite of this type here, which we can go and design. Okay, and also then once it's done that, it makes the yellow block transparent. So you don't see your baddie characters sitting inside a yellow square. They're just there as if they're free floating. So that's our startup code. Our gameplay code is another event. So on this kind of event, when a sprite of kind player overlaps a sprite of kind virus, that's these green guys here, change the score by 1, so add 1 to your score, and destroy the other sprite with a spray effect that's going to last for 500 milliseconds or half a second. And as we move our player through the environment here, indeed that does happen. You get the player disappearing and so on, or the virus disappearing. This is meant to roughly represent an antibody going after coronavirus with its characteristic spikes around its outer edge. Now you can write and run games in this simulated environment fine, and you can share them with friends and so on. But you can also, if you want to, run them on hardware. So there's a range of hardware supported by this. So you develop your code just like you did on the simulator, and you can download it into these hardware devices. They range in sophistication and price. They're usually more than about 30 euros. Here's one over here from Mouser Electronics, which is you can buy in Ireland, and it's 35 euros. This one from Adafruit, $35. If you look at the different pictures, there's a side view, there's a front view of it with a gamepad here and some LEDs in this display. This one here is the Meow bit. That's you can see the little screen in there with your character inside, and again your gamepad. And in fact, the BBC microbit is is the device inside it there, and that costs around 10 or 12 euros. Okay. So the what else have we got here? We have another one from Adafruit, which is you can buy all the various components for and build up yourself. This is the SAMD51 microcontroller and a separate display that works with it. So while these devices at the moment are a little bit expensive, being around 30 to 40 euros worth, over time prices will come down, I suspect. And one of the reasons they're so expensive, I suppose, is the processor and memory requirements are quite a bit higher for this sort of game than they would be for the Dublin Maker Badge. But as time passes, as Moore's law comes into effect and the price of everything drops every 18 months or thereabouts, we may well find that in a year or two we could put together a badge which is fully codable from MakeCode, and it will allow many more people to contribute to the program development. Now, where is the badge at this point for the coming year? Well, the hardware is in, it's being built, the software coding is more or less done, apart the low level code anyway. The higher level code as regards games have not been done. So we're always looking for ideas for new games. That's probably one of the harder bits in all of this, having the imagination to come up with a realistic game which has good gameplay. So please get in touch if you have any ideas, or if you want to send us your simulated game running in MakeCode. Thank you very much.
Thanks, Frank, for that. That was pretty cool. Big fan of MakeCode myself. Tell people about it a lot because you don't need to install anything, and it just connects it, and you don't need to buy any of the hardware. You can just try them out and see if you like them, and then, as you say, those things are quite expensive, so then you can fork out the money if you think it's really fun to use.
Exactly. Yeah.
I noticed there was a lot of questions on live chat, and you've been answering them as well. So I suppose I don't know if we're going to go through them, or we're just going to answer any new questions after that.
I think any new questions. I think it's kind of conversing.
Yeah, people can view too. Can scroll to the chat. But I was showing you this earlier. I do have the Dublin Maker sort of hanging on there. The Dublin Maker Badge from last year. The battery is slightly. I need to glue that back on. it
Yes.
went through. I wore this to every single thing I've been going to, so it went through the battles. So so it's holding on quite well. And I just want to. I think I showed you this earlier. I think you mentioned this already. One of the Adafruit I got one of the pipe badges. I'm one of those people that see something shiny.
Yeah, they're very nice. I have to
Because
say.
I'm kind of trying to learn more about electronics, but I'm more of a software person. So given that they use a lot of Circuit Python stuff, so I was just learning to program electronics with Python on this thing here. So
Okay.
so that was pretty cool.
Vicky, is this chat of ours going on the feed or not?
Yes, it is. The live
Okay,
Q&A.
there's a delay. Okay.
Yeah, there's a delay, but we can
Okay.
talk and we can bring it and it'll just stream out. It's fine. So let me see if there's anything new since. So Jeffrey says, did you port the games from somewhere or write them from scratch?
Well, I wrote them from scratch, but I will say there's a bit of a caveat there. I don't know if you can see there's a poster behind me here.
Yeah.
That was to do with a project we did in 2017 where we went to the Wexford libraries and we had a thing called breadboard games. And the children there built these breadboard games. So we had some games from that I'd written a good few years ago. So they were just ported over to the new setup.
Laura, I see you have a question there. Do you want to ask that yourself?
Sure. Sorry, Frank, I noticed at the start when you're showing off all your badges that they're really, really fantastic designs. Like, how long does it take? Not just the circuit, the electronics, because I'm sure that takes a lot in the coding, but just making the different shapes and things like that?
Well, I haven't done any fancy shaped badges. The only thing I've done kind of unusual, I suppose, is, or for me anyway, unusual, was to put in the Dublin Maker logo on the badge, which only took a few minutes really. I haven't done any funny outlines, but there's some nice videos from Adafruit that goes through how to do all the sort of weird and wonderful things with KiCad. So yeah, it's not something I've done.
Cool. Let me see what the next question would be. Jeffrey asks, any suggestions how to get badges to last longer than just the events? For example, get people to reuse them.
If you just mean mechanically last longer, well, I think being soldered will do that. But I suspect you mean more like the add-ons and further work, I guess.
Yeah, he meant add-on seems like a good way to help this. I think he just tacked on that one.
Probably if Tog were to organize an after Maker badge evening, maybe it's something like that for people to show what they've done with theirs, etc., or how to expand them. Maybe, I don't know.
I like those add-ons. I don't think I've actually seen. All I've seen was just the badges and people just program because mainly for me I've just seen them mainly at the software conferences. So I think a lot of people kind of sort of new, as opposed to a lot of kind of the hardware hacking conferences where people like DEF CON, they do a lot of hacking hardware, and seeing a lot of. I like to see kind of more examples on what people did with the add-ons, like because for me, like I kind of think, what kind of so in your what would be a simple add-on to say a badge that people can do if they got one of these?
Well, I mean. Somebody who teaches IoT a lot, I mean, you could do environmental stuff like temperature sensing and that sort of stuff. Or you could add on maybe an extra, some sort of fancy display or decoration you want to do something with, or connect it to an Arduino, a link to an Arduino to have the Arduino be a slave to it or to control it in some way. I don't know.
Lots of different ways you can do it. As I say, at the top of your head. Let's put you in the spot there.
Yeah.
So if there's any other questions, people can add. Yes, I don't think there's any questions. So I know you said you're not on Twitter, but I have been tweeting out all stuff. But is there kind of other ways that people can contact you, or just via your website?
I suppose through my email address, I guess, or through on ioprog.com, they can just stick in a comment on any post there.
Okay. So we have another question from Tomas. Okay. What sort of expansions do people do on these badges? What's your favorite expansion you have seen? So.
Yeah, okay, so Jeffrey's put in a suggestion there to Tomas's question. The BME 280 is a pressure and humidity sensor, I think, and temperature sensor. So no, not humidity, pressure and temperature sensor. So yeah, you could do that sort of thing just for looking at, I suppose, weather in some way. It's not exactly very exciting from a as a participation sport. Be nice to add on maybe some sort of something that does movement, like something robotic or something. I think that always gets a more kind of visceral reaction when you see a device being physically moved around the place.
Oh, I think I missed. Yeah, I think that's mostly all the questions right after all the ones on live chat that you've been answering. But yeah. Cool. So do you have any kind of tips for anyone who wants to? I know you did kind of like how to get into it and things like that. So if someone wants to go and try it out, like right after this, want to get some components and stuff, any quick tips, any time, like anything that you kind of say, okay, you might want to wait some time for these components, or you need to buy it from these certain places.
Well, there's two avenues, I suppose. If you're just trying it out from start and you're not done any huge experience with any of this, the likes of the badges that come for MakeCode Arcade are good. Also, the BBC Microbit is also a great starting point, and it's just about to have a new release this month. There's a new version coming out, and that has speaker and LEDs and Bluetooth, so you can integrate with your phone. So there's a lot going on with that, and it also works with Microsoft MakeCode. So if you're tackling from that point of view, yes. If you're coming at it from the, I suppose, the bottom end or the hardware end of things, go shopping on AliExpress or something like that.
Shopping list is quite hard when there's so many components, as I can see from KiCad. It's kind of quite daunting, and all the bits and pieces, and until you get used to all the component names. So I suppose for me, I'm just speaking from a newbie. Like when I'm looking at this, how do I even go about getting my shopping list together? But yeah, that'd be getting some pre-built existing ones first. But definitely, there's free. Just go in the browser and try out like a MakeCode, see what you like.
Most of these badges that I mentioned are all open source also, so they could be a good starting point. You can say, okay, well, how did they do that? And maybe you can change it to suit yourself and so
on. Okay, Tomas said, can you recommend an inexpensive soldering iron suitable for surface mount work?
Well, the one I showed you there from Farnell, that was actually quite cheap. That was only about €40, Tomas. Now it's not. I bought a very tiny head to go with it. So it's not a very high-end thing, and it does me fine for doing small amounts of surface mount. I think if you're doing lots of it, other people do things like bake on the devices using solder paste. That's not something I've tried yet. It's something I suppose I should do, but I have no experience of that.
Cool. I suppose right now it's just kind of if people want to try things at home, it's just kind of a bit annoying with the COVID that you can't just go in person, because I know I need someone to actually show me, like, especially all the close-ups, your impressive soldering kind of that you
don't drink too much coffee that day.
Yeah. But yeah, once things open up, I know TOG has kind of electronic nights and things, so it'd be once they open up, when we open up a bit more, people should drop in, and it's open to the public. But other than that, yeah, just find someone who might be able to help you with electronics, or just go in there and just take it easy and take it slow, I suppose.
Yeah,
but it's been really cool. I actually love these badges. I didn't expect you to give me, this Dublin Maker one. I didn't make it that evening, but that was really cool. I will have to fix it so that I can't be playing with it because it'll fall off.
I'm impressed it lasted this long.
But I actually missed the part where you can actually connect it with another person to play Pong. So I have to try that with another person who has that badge.
Well, I still have one, so maybe we'll meet up in real space sometime.
We'll
do that.
We'll do. Okay. All right, I think we're about to wrap up. Laura, do you have anything any more to ask?
No, I just want to thank Frank. That was really interesting.
Yeah.
Thank you. And thank you for showing us the code and how you even just designed everything,
Yeah, from the PCB and stuff. That was really interesting behind the scenes. Yeah. Thank you, Laura. Thank you, Frank, for showing us how the Dublin Maker Badge was done behind the scenes. And thank you everyone for joining us in this session. So I suppose I'll have a few words to say before we wrap up. So I will say bye to Frank and bye to Laura for now.
Thanks,
and then I'll announce them tomorrow what's happening this evening. So this evening we have the South Dublin Radio Club, where at 8 o'clock, and they'll show you how to create and then build an antenna and capture satellite images that's passing near you. So if you're interested in that, join us. Just go to our YouTube channel or Dublin Maker YouTube channel. If you haven't subscribed, please subscribe and hit that bell button so you know when the next video comes live. Because it's not this particular video, it'll be another video stream. So if you have any questions, please put them on live chat this evening as well. But do tweet us. We're Dublin Maker on. Yeah, we're Dublin Maker on Twitter, Facebook, Instagram. Any questions for any of our makers, let us know. And thank you again for listening, and we'll see you later on this evening at 8 o'clock. Okay, bye everyone.